So let's make now a few general remarks based on what we saw here, namely clustering is something you can never get the right answer because you're sort of asking a funny question. There is no correct clustering of those points. They're just different clusterings which give different results for some quality measure, such as say in Python, the quality measure they use is the mean distance between the points in the cluster centers. They want to minimize that, but there may well be other quality measures. So when you're trying to minimize a quality measure, that's called an optimization problem. And if you look at lots of things in life, clustering is an optimization problem, but so are lots of other things. And so optimization problems are by definition either minimization problems or maximization problems. Actually, they can be a little more complicated. They're so-called multi-objective because you might be minimizing three things subject to some other thing being big or some other thing being fixed in value. But let's imagine, in the case of clustering, you even see that in terms of number of clusters. You may wish to minimize some quality, but also change the number of clusters. And that makes it a reasonably complicated optimization problem. So let's imagine, usually when you talk about optimization, you talk about minimization, even though a famous optimization method is called expectation maximization. It's still true that you usually look at minimization, because then you can draw nice bell-shaped curves which are upside down, and the bottom of the curve is what you want. So now let's look at this picture here, and I've labeled it unhappiness. So we want to minimize unhappiness. That's the same as maximizing happiness. And there's some plot of unhappiness against, in the case of clustering, it's going to be against the position of the centers. And it could look like this. You may be starting up here, where it says initial position, and then maybe k-means gets you here. But k-means, when you start with a different set of starting positions, gets you here. Let's assume this is the true minimum, that this is the lowest value of unhappiness in this problem. What's the characteristic of a local minimum? The characteristic of a local minimum is the value of your objective function is higher than it is at the real minimum, and it is a nice shaped curve such that if you start at the minimum and change yourself by a small amount, you always get to a larger value of the objective function. So that's what is meant by local minimum. Small changes are stable. Large changes, if I jump from here to here and then minimize, I go down to here. So large changes are not stable. And so that's all optimization problems of this type have this problem of local minimum. And we'll see, I say, for k-means, we'll see some good examples later on for a different clustering problem. And this deterministic annealing method is actually aimed to at least partly address this problem. And it uses a methodology which we won't go through, but just to illustrate a point. We all notice the method is called annealing, or more precisely, deterministic annealing. And annealing is a idea from physics, because I told you that many things people do in life is minimizing things. Well, so does nature. Mother Nature takes the laws of physics and it minimizes things because they like to get in the lowest energy state or the lowest so-called free energy state. And if you were a blacksmith, you would know that if you had some metal and you wanted that metal to be as good, high quality as possible, and it was hot, and you just sort of made it to a particular shape at a high temperature, and then when you wanted to cool it properly, you would cool it slowly, because if you cool things too fast, the atoms in the crystal get trapped into incorrect positions, and you will not go to the lowest energy state. And typically, When you take physical systems, you cool them too fast, you get a less satisfactory material with less good properties. It's not as subject to breaking and all sorts of things. And there is an example on the left of some beads. One of them is got some clear defects, which is not annealed, and the one that was annealed, then we cool slowly. It has no artificial coloring. So another way of looking at annealing is fuzzing things up, because what happens in physics when you have a high temperature, the atoms dash around more and more at high temperature. So by allowing the system to cool slowly, you're keeping it at a high temperature longer, which means you're allowing your atoms to rush around and find the best solution. So if we go back to the previous slide, annealing essentially allows me to move the atoms, or in this case here, the center positions, quite a bit. In fact, in the algorithm, and that by doing that, you notice this smaller minimum here. Whereas if we just do things, trap things at low temperatures, where they don't move around, you're likely to go straight down to here. Only by moving things around will you find this real minimum. So that's the basic idea behind annealing. And it's just one way of addressing this issue. And this is shown in a little more detail here as to why annealing works. In annealing, you start the system off at high temperature. If you look at your objective function, your unhappiness at high temperature, you will find at high temperature there's none of this roughness, none of this structure with false minima. It's just a smooth curve. You can optimize that smooth curve, the smooth bell-shaped curve and ball-shaped curve, and you will get the correct minima. And then in annealing, you lower the temperature. That's what the blacksmith is doing. And you can see that if you're starting here and you want to find the minima, you're going to go to here, which is the minima. Whereas if you start here, which is far from the minima, and you go minimize it at this temperature, go to here. So this points out the essential idea of annealing. By minimizing the objective function at a high temperature, you'll get the correct minima at that high temperature, because there's not any false minima at high temperature. Then if you slowly lower the temperature, that minima will track the correct minima and not be tempted to go to these false minima here, here, and here, and here. So that's the idea there behind annealing. Another important idea here is greediness. You will often see so-called greedy algorithms, and greedy algorithms are the following type. They consist of iterations. At every iteration, they do the most obvious thing. Namely, they make the step the most obvious to minimize the function. That's k-means. It assigns points to the nearest center. That's the most obvious thing to do. And then recalculates the cluster center based on the points assigned to it. This effectively gives you a set of short-term optima, but it doesn't always give you the global optima. And again, that's a well-known fact of life. If you want to get your ultimate optimal solution, doing that by always locally optimizing what will happen in the next 5 minutes is not clearly going to give you the right answer. Sometimes you have to make strategic long-term decisions which are necessary to get the long-term answer you want, and a set of short-term optima will not lead you to the long-term optima. So, but greedy algorithms are very powerful, because usually they're the things you can think of and write down analytically and solve, whereas the non-greedy algorithms are not so easy.